So, good afternoon. I'm Konstantinos Baxevanakis from the National Technical University of Athens, and I'm going to present you static interactions of cracks with dislocations and dipoles of dislocations in the theory of coupled stress elasticity. This work is joined with Panos Gourgiotis and Professor Georgiadis. The motivation for this study is to investigate strength at micro and nano scales. Indeed, cracks are known to emit dislocations in order to lower the local stress density factors and are shielded by this phenomenon. Further, this interaction may, in some cases, lead to crack closure, which is an important issue in fatigue. As it has been said before in today's lectures, classical continuum theories possess no intrinsic length scales, so they cannot predict the experimentally observed size effects. For example, the stress concentration does not depend upon the size of the defect, or the J integral of crack problems also does not depend upon the material microstructure. In this study, we will employ the distributed dislocation technique, which is attributed to Bilby, and there is a great book by Professor Hills. And in the past, it proved to be an effective approach in crack problems, comparing to the well-established methods of FEM, finite and boundary element method, because it demands very little computational cost, giving a great detail of information. This is the outline of my talk. I'm going to briefly present the fundamentals of the theory. Then I'm going to talk about dislocation fields in coupled stress theory. And next we will present the modeling of cracks using the distribution of dislocations. And we will study the static interactions with both plane and anti-plane defects. Next, we will present the formulation of crack problems using dislocation dipoles, and we will study the interactions with dipoles as well. And finally, we will evaluate the configurational forces on the defects. So, the point of deviation from classical theories is that in the Euler-Cauchy principle is augmented with non-vanishing coupled stress tensor, and in this theory the constraint Kozer elasticity, the strain energy density depends upon the gradient of a rotation vector. We also note that this theory is different from the general Kozer theory in the sense that the rotation is constrained, and also is different from the Tupin-Mindlin graded elasticity theory. So these are the balance laws in the absence of inertia effects here and body forces and body couples, where this term is the moment traction. Now, pertinent force or total stress and coupled stress tensors may be introduced by considering the elementary material tetrahedron. Enforcing the previous balance laws, we derive the equations of equilibrium. Now, as for the kinematical description, in the geometrically linear case, we have the usual quantities of classical theory, and here the curvature tensor is introduced as the gradient of the rotation. And we write this form for the strain energy density for a linear and isotropic constitutive behavior. Now, in the standard variational manner, we derive the stress and coupled stresses under these forms, where the Lamé constants are involved, and also these terms that are the coupled stress moduli expressed in dimensions of force. And we have these restrictions for the material parameters in the to ensure a positive definite strain energy density. And also, in light of the above, we have the displacement equations of equilibrium under this form. Now, in plane strain cases, the non-vanishing components of the asymmetric force tensor and coupled stress tensor take these forms, and the displacement equations are coupled PDEs of the fourth order, where when the material microstructure vanishes, we derive the classical Navier-Cossy equations. And in the anti-plane case, we have these terms for the total stress and the coupled stress tensor. And now we have a single PDE for the displacement components. Now, going to the distributed dislocation technique, its concept may be demonstrated in this slide by considering a simple mode 1 crack. The solution to the problem will be obtained by superposition of the two auxiliary problems here in figures B and C. That is, the stresses arising in the uncracked body and the stresses that are induced in the unloaded body due to the application of equal and opposite tractions to those of problem B. Now, in order to apply this technique in coupled stress theory, we first have to derive the stress fields for a climb dislocation, a glide dislocation, and a screw dislocation. Those fields are obtained by solving half-space problems and applying Fourier transforms. And we finally get these solutions for the dislocation slip plane. And in the red boxes we have highlighted the classical solutions. So what we see is that in the case of a climb dislocation and a screw dislocation, we have both stresses, here normal stresses and here shear stresses, and also coupled stresses. Whereas for the glide dislocation, we have only shear stresses and no coupled stresses. Now, going to our first example here, this is the interaction of a finite length crack with a climb dislocation, which lies at a distance d from the center of the crack. These are the boundary conditions, and in the classical theory, this crack would be modeled by a distribution of climb dislocations. Here this is not the case because, as we saw in the previous slide, a distribution of climb dislocation would produce coupled stresses. So we need to cancel those stresses, and this problem is solved by distributing additional rotational defects that in the past Bourgiotis and Georgiadis have named constrained wedge disclinations. So in order to obtain the Green's function of the problems, we solve these boundary value problems, and by superposition we have these fields. So this is the contribution of climb dislocation in these terms, and this is the contribution of this new defect, mathematical defect. In order to feel what this defect is like, we have made the comparison in this table. In the left is a standard wedge disclination where a jump in the rotation induces discontinuity in the displacement, and in the right column is the constrained wedge disclination, which we would like to mention that resembles the concept of crystal twinning. This is a picture of crystal twinning. So finally, by distributing these defects, we obtain this system of coupled singular integral equations that have Cossy and logarithmic kernels. And also, in order to have uniqueness of the normal displacement and the rotation, we have the closure conditions under these forms here. The densities of the integral equations represent the slope here and the curvature. And also we have regular kernels that obtain modifiable Bessel functions and a Meyer function here. Taking into account the asymptotic behavior, we write the densities under these forms, and finally the singular integral equations are solved using the collocation method. Now, some results. In the left figure we have the upper half crack displacement profile due to the interaction with the climb dislocation for various values of A over L. here. What we see here is that as the material microstructure becomes comparable to the crack length, the material exhibits a more stiff behavior here, and that the classical theory with the dotted line serves as an upper bound for coupled stress theory. And on the right figure we have plotted again the displacement profiles for various dislocation positions. Here we also plot the rotation, the crack rotation. So what we see here is that the produced fields are bounded on the crack tips, contrary to the prediction of classical theory. This is the stress distribution and the coupled stress distribution. We see that we have coupled stress effect dominant within a zone of 3L here and 5L near the dislocation core. I would like to mention that both these fields remain unbounded in the dislocation in the coupled stress theory. And these are plots of the stress intensity factors for both crack tips. The continuous line is for the right crack tip and the dotted is for the left crack tip. What we see here is we have a boundary layer here as L tends to 0 because we do not reach unity, and also we have an asymptotic value as L over A tends to infinity. We also derive the energy release rate in this case, which takes this form, and we also consider the rectangular shaped contour, which was inspired by a friend, and some products of singular distributions here. And these are the results again for the right crack tips and the left crack tips. What we see here is that this ratio goes to unity as L over A tends to 0, so the transition to classical elasticity is continuous, and also decreases, reaching a bounded minimum here, and then increases with this asymptotic value. This means that we have a strengthening effect at this region, and then we have a weakening effect for the other values of L over A. Just a quick comparison with the interaction with a glide effect. This problem is governed by a singular integral equation. And we have these results for the stress intensity factor on the left and the J integral ratio on the right. We see that here we have a larger increase in this ratio of the stress intensity factor, and we observe the same phenomenon as earlier for the J integral ratio, with the strengthening region and the weakening region. Now, going to the anti-plane case, here we have a crack interacting with a screw dislocation. These are the boundary conditions again. All fields, as usual, vanish to infinity. In this case, we have this asymptotic behavior, which is smoother behavior. And we obtain one single hypersingular equation with this regular kernel. So after solving this problem, we plot the crack face displacements. The first statement still exists, that we have a stiffer behavior, but also we have cusp-like closure in the crack tips. We have plotted it here. And on the right figure we have plotted the total stress distribution. What we see is that very near the right crack tip, this total stress exhibits negative values, thus exhibiting a cohesive traction character. And also we have a boundary layer behavior of this kind. Again, we plot the J integral results. In this case, we see that in all range of L over A we are above unity, and thus in the anti-plane problem a strengthening effect is predicted throughout this range of material parameters. We also note that these curves tend to 0, and this is because of the nature of the loading as we plot here, for various values of the couple stress moduli and the A over L, this loading changes sign. So this is a peculiar statement here. Now, an alternative way to model cracks is by distributing dislocation dipoles. What we have already seen is this figure, where we have distributed dislocations, and the crack opening profile was represented by a stack of thin strips. Now the same boundary value problem may be obtained by distributed dipoles, and the crack opening displacement will be represented by an array of narrow strips, which are called infinitesimal dislocation dipoles. So the first thing was to obtain these fields in couple stress elasticity for both the infinitesimal and the finite dislocation dipoles. So these fields are obtained by the superposition of opposite sign dislocations separated by a distance, namely W here. And this is an example from classical theory of elasticity. In the finite dislocation dipole, this term here remains, where in the infinitesimal it vanishes. And also we have to obtain the same fields for a glide, a horizontal glide, and the horizontal screw dislocation dipoles. Now, when we construct, we study the interaction with climb defects, we end up with a system, a coupled system of hypersingular integral equations. Now, we have these hypersingular terms. And now the densities represent directly the displacement and the rotation, taking into account the asymptotic behavior, which is the same as earlier. Before studying the interactions with dipoles, we have made a comparison. We have solved the same problem as before, and that is the interaction of a crack with a single climb dislocation, in order to compare the two methodologies. And as we see, we need, in this approach, we need less number of terms for a given degree of accuracy. And also we have written. Sorry? Yes. Yes, we plot here the values of this ratio. Yes, using both approaches. So we have written some advantages of this methodology that are reported by other authors as well. The most obvious is that this methodology is more direct, because we do not need an extra step of integration to obtain the crack phase displacement, and also that the displacement is bounded everywhere, obviously, whereas the slope is unbounded. So these are some results using this approach for the interaction with a horizontal climb dipole. We report basically the same behavior as before with the dislocation. So the dipoles and the dislocation dipoles behave in the same way. We have a boundary layer behavior here, and as for the J integrals, we have the strengthening and the weakening ranges there. And the same stands for the interaction with the glide dipoles. Again, we have a single hypersingular equation, the same behavior. And in the anti-plane mode, we have this hypersingular integral equation. In order to solve this problem, we need to calculate some hypersingular integrals, and basically we report the same behavior. Now, each approach of this kind should contain the evaluation of configurational forces on the defects. So this definition based on stresses is given under this form, and also the pitch scalar force can be defined as the gradient of the strain energy with respect to the defect position, which is the J integral on a dislocation is the pitch scalar force. So we consider the contours around the defects and the crack, and we obtain these equations of equilibrium here for the case of a dislocation and of a dipole. And here we have plotted the ratios of the pitch scalar in this theory over the classical results for interaction with a climb dislocation and a climb dislocation dipole. Basically, this response is the same as the J integral behavior. Yes, I'm finishing, yes. This is my final slide. In the most general case, the dislocation may lie off the crack line and also may have a random orientation. So in this case, we will have a mixed mode problem which will need a distribution of climb and glide dislocations and these rotational defects in order to be modeled. And we report that for some positions of the defects, crack closure may occur. And here I have put a diagram for interaction with a climb dislocation. Here we see that for this interaction, we observe in the classical theory crack closure at 53 degrees. But as the material microstructure becomes more prominent, we see a great range of results. That is, here we have crack closure at 64 degrees. So some concluding remarks. The main concern in this study was to determine possible deviations from the prediction of classical linear elasticity when more refined theory is employed for crack problems. In several cases we observed a more natural behavior with bounded results and more smooth crack closures. We also note that the stress intensity factor in this theory is always significantly higher, and also we have observed a boundary layer behavior. Whereas for the J integral ratio, we noted that the transition to classical elasticity is continuous, and in the plane cases we observed strengthening and weakening effects depending on the microstructural parameters, and in the anti-plane mode we predicted a strengthening effect throughout the range of microstructural parameters. So thank you for your attention.
You introduced or you discussed line and screw dislocations.
Yes.
Up to now I decided edge and screw dislocations. So what's edge dislocation? Maybe glide.
Well, an edge dislocation may be either a climb or a glide.
So what's the difference between glide?
It's just a difference in orientation. So a climb would be, say, having a Berger's vector of 0, by, and a glide would be bx, 0.
That's edge dislocation.
Yes.
Climb and glide are motion dislocation.
Well, I mean, this is a definition in Hill's book. Maybe it's a jargon. Yeah.
Glide and climb are about the motion and dislocation.
Yes,
Not about their nature.
yes, I know. We have adopted these definitions. Yes, I agree. Yes, they are both edge dislocations.
If you assume that stress around the dislocation is obtained by elastic effect, what I have understood is that there is a coupled stress theory everywhere, but the stress is obtained just by elastic.
You mean the stress fields of the defects?
Induced by the dislocation.
No, the stress fields actually, in some cases, they are reported by other authors. They are obtained by airy functions. But here we have solved half space problems. So we have applied all the tractions and solved the boundary value problems for the half spaces.
So you said that you used the closure condition around the crack too? Is that true?
Yes, this is standard, yes.
But there is a closure defect, there is a crack.
There is a defect?
There is a closure defect. That is, you cannot use a closure condition because there is a closure defect. There is a discontinuity of displacement, or there is a discontinuity of both, discontinuity of rotation. So there is no closure.
Yes, but after all, I mean, if you take the integral, in the end, it should be closed. Because our defect is discrete lying somewhere else. This would be the case if the defect lied right at the crack tip. In that case, we would have no closure condition. But when it lies somewhere away, the jump is...
When you are away from the crack,
yes, this is what I presented here. Otherwise, I agree, yes. If I put it right at the crack tip, no closure would help.
I have a question.
Yes.
Did you investigate the dependence of your solution upon your constitutive parameters in the curvature expression? You have assumed positivity of all factors, which is not necessary for uniqueness of the problem. You can have positive semi-definiteness in the curvature expression, which makes for symmetric stresses in the theory. You can have a coupled stress system with symmetric stresses, local stresses and higher order stresses. But did you investigate the dependence of your solutions on what kind of curvature expression you assume?
No.
So what did you take? Just what was your curvature expression in solution?
Curvature.
The higher term. The energy going on the gradient of the curve.
Well, I'm not sure.
The eta. I think the eta is it in your description.
The eta is in the anti-plane mode? Yes.
There's a parameter which, apparently you didn't do it.
For the Baxevanakis case considered here, there's also only eta, which is related with L, the characteristic model length.
Yeah, but there are two.
Yes.
Okay, you have it.
Because it has more critical.
And what did you use for this?
For the anti-Baxevanakis case, there is the ratio that has to be from -1 to 1 in order to be positive there. However, we went limits of -1 to 1.